Hey guys, this is continuing on with VSEPR theory, so this is part 2. Make sure you're filling in the notes as you watch this video. So, valence bond theory includes the following principles. You have to know how to do the Lewis dot structures, which is going to tell you where those valence electrons are among the atoms in a molecule. And then we have VSEPR theory, which is what we're using to predict the geometry of the molecules. And then there's something called hybridization theory. That describes the type of atomic orbitals used by the atoms to share electrons or to hold lone pairs. So hybridization is more about the orbitals and kind of what they look like. So this chart is going to be really helpful for you, and we'll come back and forth to this in a little bit. If you're in class, you also have a handout of these. If you're at home, you may take a screenshot of this so that you can come back and look at it when you need to. So basically, it tells you your pairs of electrons, how many that are bonded. And then it also is going to tell you how many unshared pairs, so lone pairs, and then it'll give you the shapes or the geometries. So again, I showed y'all this slide last time. These are the main basic shapes or geometries that molecules will make. The main ones you need to know are linear, bent, trigonal planar, triagonal pyramidal, and tetrahedral. Those are the most important ones for this class. So to determine geometry, first we need to know the difference between electron geometry and molecular geometry. Electron geometry is going to be the shape of all the electrons around that central atom, whether they're shared or unshared. Molecular geometry is just the shape of the atoms of the shared pairs of around the central atom. So these shapes form because valence electrons repel each other. So electrons are trying to get as far away from each other as they can. So here's some examples. I have in PCl3, we talked about this one last class, and we drew out the Lewis dot structure, so that's what that diagram is. It also has the partial charges. It also has the dipole arrows on there in black. So just by looking at the Lewis dot diagram, I can see that there's 3 shared pairs of electrons. So those are the lines between Cl and P. And on that central atom, the phosphorus, there's 1 unshared pair. So that's your lone pair of electrons. So if I'm using that chart that we were just looking at, I have 3 shared pairs, I have 1 unshared pair. So the electron geometry would be tetrahedral. The molecular geometry would be trigonal or triagonal pyramidal. So those are the 2 geometries that you would see for this element. Molecular geometries that are symmetrical will cancel out the charge on the atoms, and we mentioned this a little bit last class. That means the net dipole moment of the entire molecule is 0, meaning the center of negative charge lies on top of the center of positive charge of the entire molecule, so there's really no charge at all. So anything that's symmetrical doesn't have a dipole moment really, because it's all going to cancel out. So you wouldn't draw the arrows on nonpolar or symmetrical elements or compounds. In this example, the molecule is not symmetrical, so we say this molecule has a permanent dipole moment. That also means it's polar. The center of the negative charge, or the net sum of all the slightly negative atoms, would be somewhere underneath that phosphorus atom. So let's do another example. In this example, I have CF4. So the first thing you need to do is draw out your Lewis dot diagram. I did that for you already. So those arrows could also indicate that there's a bond going between carbon and fluorine. Once you do that, you can write out your charges. Carbon is the one with the fewer amount of electrons in this case. So carbon is going to have that partial positive. Fluorine is gaining an electron, so it has partial negatives. My dipole arrow would go towards fluorine because that is more electronegative than carbon. Remember that because there's a difference in electronegativity, I have a polar molecule right now. All right, so if I was going to try to figure out the shapes or the geometries, I'm going to look and see that I have 4 shared pairs of electrons around the carbon and no unshared pairs. So if I'm using that chart or the handout that you have in class, I have this tetrahedral shape for both the electron geometry and the molecular geometry. In this example, the molecule is symmetrical, so it doesn't have a dipole moment. The shape of the molecule cancels out all the individual charges. So in this case, we really don't need to draw those partial charges, and we really don't need to draw the arrows. There's no dipole moment. It's non-polar. So it has no permanent slight charge. So again, we mentioned this last class, if it's a symmetrical compound, even though it has an electronegativity difference, we're going to go ahead and call this nonpolar because it's symmetrical and those charges can cancel out. So here's a list of those kind of weird shapes where the dipoles cancel, or where the charges cancel, and where it's just, there's no dipole moment. You don't have to draw the arrows. So it's all of these shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, square planar, and octahedral. All of those are symmetrical. It's also important to note, in order for a particular molecular geometry to cancel out slight charges or partial charges, all of the outside atoms have to be identical. So part of being symmetrical includes having the same elements on the outside. So here's an example, CF2O. This has 3 shared pairs and no unshared pairs around that carbon. But if we're counting bonds for trying to figure out the geometry, double and triple bonds are just going to count as 1 shared pair. So instead of saying I have 4, I'm just going to say 1 because one of those is a double bond. If we look at our chart, the electron geometry for this is trigonal planar, and the molecular geometry is trigonal planar. The difference in electronegativity is going to be 0.89, but the difference in electronegativity between C and F is 1.43. They result in different dipole moments, and there's a slight charge. So the shape isn't canceling out in this case because I don't have fluorine on every side of the carbon. That oxygen is changing up the symmetry a little bit. We say that this molecule has permanent dipole moment and it's polar, so it has a permanent slight charge. Okay, that's it for this set of notes. Those short and quick. You have some practice problems to do in class. It involves building some of these atoms. If you're at home, do what you can. You may have to end up just kind of drawing them on your paper rather than building the models. Otherwise, you can ask someone in class to send you pictures of the atoms and the compounds that you